next speaker, Mihir Sheth. He will talk to us on locally analytic representations and p-adic Langlands problem. Mihir, start.
Yeah, thank you very much, and thanks to organizers for giving me the opportunity to talk about my work in this symposium. So this is going to be an overview talk on the theory of locally analytic representations in the context of p-adic Langlands program. And in the end, I will mention my result from my PhD work, but most of the talk is an overview talk. Okay, so let's begin. So let K be a finite extension of QP, GK be the absolute Galois group of K, and WK be the while group of K. So the story begins with the local class field theory. So the local class field theory is a statement about connection between the local field K and its abelian extensions of K. So local class field theory gives a map from K cross to the abelianized Galois group, which induces isomorphism onto the abelianized Weyl group. That means the Weyl group modulo its commutator subgroup. So this is a sort of this is kind of a link between the abelian extensions of K and the data which is intrinsic to the field K itself. And so local Langlands correspondence is a generalization of this fact to higher dimensions. So from this isomorphism, we see that one-dimensional representations of the Weyl group are in one-to-one correspondence with the smooth irreducible representations of K cross, right? That is JL1K. And this can be generalized to the higher dimensions, and then we have a so-called classical local Langlands correspondence. It's a one-to-one correspondence between certain n-dimensional representations of the Weyl group K and smooth irreducible representations of GL and K. Now it's not just any correspondence, but it satisfies certain properties. In particular, this one-to-one correspondence is compatible with the local class field theory in the sense that on the right-hand side, if I look at the central character, it matches with the determinant character of these finite dimensional representations of the Weyl group via this isomorphism. So this extends the local class field theory to higher dimensions. And also note that on both sides of this correspondence, I do not mention the underlying base field of the representations because on both sides we consider smooth representations. Here I say certain n-dimensional representations, but they are basically smooth representations of the Weyl group. And here are also smooth representations of the general linear group. So the base field does not matter. But when we speak of Galois representations, which is a natural source for the Weyl group representations, the base field plays an important role. So over complex vector spaces, this classical local Langlands correspondence restricts to continuous n-dimensional irreducible representations of the absolute Galois group, restricts to the correspondence between continuous representations of the absolute Galois group and smooth irreducible supercuspidal representations of the GL and K. We saw the definition of supercuspidal in the previous talk, so maybe audience might be familiar with this. Okay, so over complex vector spaces, we do have a sort of bijection between Galois representations and the representations of the general linear group. But if you look at the structure of this Galois group, which is the absolute Galois group of a local field, it has a closed subgroup which is a pro-p group. The wild inertia group is a pro-p group, and therefore the complex representations of this GK do not give much information of this Galois group. So if we look at the continuous representations of this Galois group on p-adic vector spaces, so that means on vector spaces which have the same local topology as the absolute Galois group, then we will get more information of the Galois group itself. Okay, so do we have such a correspondence then over p-adic vector spaces? Unfortunately, over p-adic vector spaces, however, there are too many continuous Galois representations. That is understandable because, as I said, the topologies of this Galois group, topology of the Galois group GK and GLN of p-adic field are compatible. So there are too many continuous Galois representations. That means on the left hand side is we need to have some sort of control on the left hand side, as there are too many representations on the left hand side. Or in other words, we need to enlarge the category on the right hand side. So it is naive to consider any sort of p-adic correspondence uh, with with the right hand side consisting of only smooth representations. We have to sort of look for other type of representations of the general linear group. Okay. Nevertheless, there is a p-adic analog or extension of the classical local Lagrange correspondence when n is equal to 2 and k equal to qp. And let's see what is this. So let rho be a absolutely irreducible crystalline representation of Hodge state weights 0, k minus 1 over a p-adic field L. Okay, so here I am considering the representations of the absolute Galois group of QP over a two-dimensional representations over a p-adic field, that is some finite extension of QP. And as I mentioned, these representations have rich structure. So that is sort of described by these data that it is crystalline and Hodge state weights 0, k minus 1. But you don't need to worry if you don't know these notions. But it is just some additional data associated with this p-adic Galois representation. And using this additional data, we now construct a GL2QP representation that is just the tensor product of the symmetric k minus 2 for representation of L2 and a smooth representation that comes from the classical local Lagrange correspondence. Now, since rho is a nice p-adic Galois representation, one can associate to rho a classical Weil-Dirichlet representation. And by classical local Lagrange correspondence, it corresponds to some smooth representation of GL2QP. So this pi smooth is that Weil group representation. And then we consider, not Weil group representation, but it corresponds to Weil group representation, pi smooth under classical local Lagrange correspondence. And then we consider the tensor product of this pi smooth and symmetric power representation, and let's call this pi rho alge. And it's a fact that this GL2QP representation admits a unique Banach completion. So there is a GL2QP invariant norm on this pi rho alge, and the completion of this with respect to this GL2QP invariant norm is a Banach representation, which is also topologically irreducible, admissible, and unitary. And this gives a correspondence between, this is, so generalizing this to more general types of irreducible two-dimensional representations of GQP gives a correspondence which is over p-adic fields. So this is a p-adic local Lagrange correspondence, which is again a bijection between two types of representations. On left hand side, I have continuous irreducible two-dimensional representations of GQP over a p-adic field L. And on the right hand side, I have certain Banach space representations of GL2QP over p-adic field L. So this is an extension of the classical local Lagrange correspondence to p-adic fields, because you see the information coming from classical local Langlands correspondence is already there in this periodic Langlands correspondence. So this sort of extends the classical local Langlands correspondence. And the representation that we construct here from the data of the periodic Galois representation is an instance of a locally analytic representations. So now I come to the definition of a locally analytic representation. So as the name suggests, it's a continuous representation of a periodic Lie group G. So like GL2QP, for example, in this case, on a topological L vector space V is locally analytic if some open subgroup of G acts analytically on V. So that means if you look at the orbit map for each vector in V, if you look at the orbit map from G to V, which sends small g to small g acting on V, that orbit map is given by is analytic. I mean, you can make sense of analytic maps because it's a Lie group over periodic fields. Okay. So what are examples of smooth locally analytic representations? So classical smooth representations of periodic Lie groups are locally analytic because the orbit map is locally constant. Locally algebraic representations. Here the orbit map, here G acts sort of algebraically. So of course it also acts as analytically. And this pyro-alg on the previous slide here, it's an example of a locally algebraic representation. It's a tensor product of algebraic representation with the smooth representation. So if my periodic Lie group is a very nice group like the additive group ZP, so a compact and abelian group, then any continuous character, L-valued character is in fact locally analytic. This is a theorem due to Amis. So this says that if my group is nice, then the locally analytic characters are sort of familiar objects. They are just continuous characters. Then there is a analog of principal series, well, parabolic induction of locally analytic representation, and then you can talk of principal series representation, and then you also have a locally analytic Steinberg representation. That is just the L-valued functions on the projective line modulo the constant functions, locally analytic functions. Yeah, I take. Now, it was observed by Morita that this locally analytic Steinberg representation is in fact isomorphic to something coming from geometry. And this is the representation realized on the topological dual vector space of the space of differential one forms on Drinfeld's upper half plane. Recall that Drinfeld's upper half space, so upper half plane is one-dimensional Drinfeld's upper half space. So in general, n-1 Drinfeld's upper half space is nothing but the projective space n-1 dimensional. You consider the complement of all the k-rational hyperplanes in this n-1 dimension of projective space. Now, GLN K of course stabilizes this set of k-rational hyperplanes, and therefore there is natural action on this Drinfeld's upper half space. The GLN K acts on this Drinfeld's upper half space, and therefore it acts on any equivariant vector bundles on. And if you consider the global sections of such equivariant vector bundles, they gave sort of first geometric examples of locally analytic representation. So here we consider omega 1, capital omega 1. So it's the sheaf of one forms, and the global sections are basically the space of one forms on the Drinfeld's upper half space. All right. So this Drinfeld's upper half space Y0, there is a formal model of this. That's a formal scheme, and that formal scheme parameterizes deformations of certain P divisible groups. So it's a deformation space, and then there is a space X0 which parameterizes deformations of the dual data to this data, which is parameterized by Y0. And this X0 is called the Dubintet modular space, and so it's sort of dual space to the Drinfeld's upper half space. And if you look geometrically, it is nothing but the open unit disk over a periodic field of some dimension. So the poly disk even say. So let me explain the duality between Lubin-Tate space X0 and Reinfeldt's upper half space Y0. So here I have considered some Galois covers of these spaces. So as I said, X0 and Y0, they are both deformation spaces of certain PD visible groups, right? And if you consider torsion points of these fixed PD visible group that these spaces deform, you get uh, the covers, étal covers of these spaces. So these XM and YM are étal Galois covers of these X0 and Y0. X0 is the Lubin-Tate and Y0 is the Reinfeldt's upper half space. And on X0, I have the action of the automorphism group of the PD visible group that is being deformed, and that is isomorphic to the group of maximal order of the division algebra over K. And also on Y0, there is the automorphism group of the PD visible group that is being deformed by Y0. And in this case, that automorphism group is isomorphic to the maximal compact subgroup of GLNK, the standard maximal compact. And the duality is reflected uh, in this picture in the sense that if you look at these Galois covers, the Galois group here is in fact isomorphic to G0 mod GM, where GM is the mth principal congruent subgroup of this G0. And the Galois group on the Drinfeldt's upper half space side is isomorphic to the J0 mod JM. Again, JM is the congruent subgroup in the maximal order of the division algebra. So, as I said, the equivariant vector bundles on the Drinfeldt's upper half space and its étal covers gave rise to locally analytic geometric examples of locally analytic representations. So in my PhD thesis, I considered the problem whether equivariant vector bundles on Lubin-Tate space also gives rise to local analytic representations or not. And it is indeed true that it's a theorem due to my advisor and myself that the dual spaces of the structure sheaf of XM are local analytic representations of the J0, the automorphism group of the PT visible group. And the local analytic representations coming from the Drinfeldt's upper half space show up in the geometric realization of the periodic local Lemons correspondence. So here their connection with the periodic local Lemons program. But the
Excuse
relevance
me,
from
Mihir, hello. Yeah, just a request to finish it in 2 minutes because we are running out of time.
Yes, this is my last sentence.
Okay, sorry.
Yeah. So the locally analytic representations from these Drinfeldt's upper half space do show up in the geometric realization of the periodic local Lemons correspondence. And the relevance of those coming from the Lubin-Tate to the periodic local Lemons program is yet to be discovered. And, so here are some references for the interested people. And thank you. Yeah.
Okay, let us thank Mihir for such a nice talk. Now it's time for some quick questions. If people have some questions, they can just unmute and ask the questions.
Hi, Mihir.
Hello. Hi.
So you have said that the Lubin-Tate tower, the representation of J0 is locally analytic, right?
Yeah, right.
So can we do slightly more by saying that is in fact rigid analytic or something like that?
Um, one can think whether the action extends to the rigid analytic group and group underlying the J0. That's what your question is, right?
Right.
Yeah, so there is a student of Matthias Strauch who considered the rigid analytic action on this Lubin-Tate space, and he shows that. So as I said, this X0 is a like open disk of radius 1, right? He
Right.
says that on certain disk of radius strictly less than 1, the action of J0 in fact extends to the rigid analytic group, but not to the whole disk.
I see.
Yeah, that's what I know about this. But so
Yeah, thank you.
yeah.
Okay, so if there is no other questions, let us thank the speaker once again. Thank you, Mihir.